Okay, let's talk about this one. First of all, it's all about using Taylor's theorem, and I know this came off of the handout, which didn't didn't copy as well as it should have. But this is the theorem in here, and one important it looks familiar to us already. We can see that this looks like our Taylor polynomial in here. This is the nth Taylor polynomial. And then there's a term on the end here. This is called the remainder term. Okay. Taylor proved this theorem, and this term out here, it exists for some z in a neighborhood of c and x. Okay, it's between c and x. There's a number z somewhere in there, such that this term exists and encompasses the remaining portion of this function. Okay, so one term can do that. It can take up all of the rest of this remaining function for some value of z. Now, what we're going to use this for is this. The fact that this is going to be, this remainder can be no bigger than this product, the x minus c absolute value of that product, x minus c to the n plus 1 over n plus 1 factorial times the maximum of the derivative in here at some value of z. So we could say that it has to be true because that's the nature of the derivative in here. So there is some maximum, and this is it, if we can find it. So we can use that if we can find it. We got to put a bound on that derivative. That's the idea. So over here now, in this example, number 4, we're given this way of approximating cosine of 0.3. It's using the fourth Maclaurin polynomial here to get that approximation. Now the question is, how good is it? Well, we can say we're going to have our remainder term on the end here, evaluated at 0.3, and the cosine itself, the one that we're using here as an approximation, looks like this. So without that remainder, we just have this. So it's not going to be equal to the cosine of 0.3, but it'll be off a little bit. How much? Well, we can bound that error. We don't know exactly by how much, but we can say that it'll be less than or equal to the remainder term at evaluated at 0.3. That is bounded by this term here. So that is less than or equal to this. Okay, that's the idea. Okay, so this is actually equal to this remainder term here. That's equal to that. But we're going to bound it this way. So we just need to figure out the maximum of the sixth derivative here. Okay, well, I did the derivatives in here and I got 6. It's a negative cosine. Well, the cosine, we want the maximum of the absolute value of that derivative. So we're just looking at the cosine, which looks like this. And it has a maximum of 1 and occurs at x equals 0. So since it's decreasing in this interval up and here up to 0.3, is somewhere in here, the small window here, before it gets to the x axis back here. It's decreasing, so its maximum will be right at 0, and it'll be a 1. So we can use a 1 in place of this in our bound term here. So if we put that in, we get this number. So we're finished. But what I did was a little bit extra here. I wanted you to see that now the actual calculator value, which in itself is an approximation, which we're not going to go into. We're going to assume that that's the gold standard, what's coming out of the calculator, is as good as you can get. So if we assume that, then our estimate, that's what the calculator gives. And our estimate is this. That's using the first, just those first 1, 2, 3 terms there in that expansion. We got this. The difference between these is this much. Okay, if you find the difference between these, you'll get this. So the question is that less than the, well, let's see, no. That is our actual error in this case. And the question is that less than the predicted value? This is the predicted value, the bound on the error. And you'll notice that this is less than that number. This is 10108. This is 1012. So our number that we got is actually within that predicted bound for the error. Okay, so that's the idea. Now, on the next problem here, I did some more work. This will save a little bit of time, but we're trying to figure out what degree is needed to keep the error on this estimate, whatever this is, keep that error less than 0.001. Well, what that means is that we're going to find the bound here on this remainder term. So this remainder term has to be less than or equal to the maximum of the n plus first derivative, evaluated at z, where z is somewhere between x and c. Okay, somewhere between x and c. In this case, x is that number, 0.6. So somewhere between 0 and 0.6. Okay, that's where the z is going to be, somewhere in there. Now, and we could use the endpoints if it works to our advantage. And if it gives us a more conservative estimate, then we can certainly use the endpoints. Now, if I set up this inequality here, and I go in and find my maximum now, and to do that I have to look at my derivative. This one's easy because f is its own derivative, so it doesn't matter how many derivatives you take, you still get e to the x. So that's going to be true whether this is a 6, 7, a 10, or whatever. And if you look at this function, it has a maximum. E to the x looks like this. And it will have a maximum on the right side of the interval. So if we're going between 0 to 0.6, then it certainly will never get bigger than e to the 0.6. Okay, so we'll use that over here, e to the 0.6. This is, right here, this is a conservative bound for that, and it'll never get bigger than that. So we throw that in with our, now this c is 0, and x is 0.6. So I have this inequality now. Now this one, you really just can only solve this using trial numbers for n. I tried n equals 4 and I got this. And I noticed that was not less than this number. I wanted this to be less. So I had to take n equals 5, in which case I got this number, which is less than 0.001. So 5 is a safe bet. Take the fifth degree Maclaurin polynomial and use that. And that'll guarantee that your error is no bigger than 0.001. The fact is, if you do the checking here, when n is 4, I checked it. I checked this value, which comes from the calculator. Okay, take that and subtract the fourth Maclaurin polynomial results here. You get this number. That's the error of this estimate. That actually is less than 0.001. So we could have used 4, but the theory says use 5. It's a conservative estimate, guaranteed to work. We weren't sure if 4 would work. I tested it for the fun of it. N equals 5 gives a really low error, which is way below the threshold, 0.001. It's way below that. So you can see we got a really conservative estimate here by using 5 terms as our approximating polynomial, 5th degree. Not 5 terms, it's actually 6 terms, but it's 5th degree. So we could have got away with n equals 4, but the answer is n equals 5. So you would report this as your answer because of this result that we saw here. In fact, as you can stop right here, what I did down here was just a little conceptual explanation of what all this means. What does it mean?